Hello guys. In this presentation I'll be discussing about my project which is a subset of Nios-II architecture. Basically Nios-II is a soft processor made by Altera which the users can implement on an Altera FPGA board. Well, firstly it is imperative to know that what is the architecture, a block diagram of the Nios-II processor. Nios-II is a 32-bit 5-stage pipeline processor. Pipelining basically increases the throughput of the processor, and now uh, it is once it is made a five-stage pipeline processor, it has different stages to do different works, whereas it would be doing all the work in one cycle. Now it will be requiring 5 cycles for each instruction. But once after 5 instructions, every instruction will be executed in single cycle. So the five stages are as follows: the instruction fetch stage, then the instruction decode stage, then the execution stage, then the memory read write stage, and the write back stage. Okay, let's go through all the stages one by one. Firstly, the instruction fetch stage. In this stage, the instruction is fetched from the instruction memory. The program counter PC counts to the current instruction, and the NPC, which is the next program counter, counts to the next instruction. So basically, what we do is we decode the instruction from the instruction memory using the NPC, and we constantly add +4, that is 4 bytes to the PC to get the next instruction, because it is a byte addressable memory and every instruction takes 4 bytes. So that is why we add +4 to the PC. Well, the second stage is the decode stage. In this stage, basically all the instructions are decoded, and part by part it is understood what is to be done with the instruction. All the registers and the opcodes are obtained in this specific stage. For example, as you can see, there's RD, WE, RA, RB. Now RA, RB are two registers. We can call them as operands when we have to deal with them in the ALU. So they go straight to the ALU. The ALU or the execution stage actually decides what is to be done with them, like whichever of them is to be picked up for operating. Then there's an immediate value. There are some kinds of instructions which take direct value from the instruction rather than going to the register file and then picking up any single value out of it. So the IMM over here points to such specific value that you can give to the ALU through the instruction itself. Now the instruction carries only 16 bit of immediate value, but the ALU is a 32-bit ALU, right? So what we do is we extend the 16-bit into 32-bit. It's called the sign extension basically. So now we have all the registers and the operands. So the next stage is execute stage, where the ALU actually works. Now there are two registers over here you can see, which is A and B. Now these are the A and B values are coming from the register file after we give the address of the registers. That is the source and the target register. And then this is the IMM, which is the actual value. This is the immediate value that you can use for operating on the ALU. So the ALU decides based on the opcode what you have to what it has to do basically with the operands. So the opcode also is given by the decode stage after decoding from the instruction. Now let's move on to the next stage, which is the memory write stage. Oh yes, so the ALU has done some operation taking the operands and the opcode. So now the result of the ALU has to be written either in the memory or back to the register file. So this stage deals with only the memory. So if we have an address and if it points to the memory, then the ALU, the output of the ALU is written in the memory. Like for example, there are some instructions like the SW instruction in MIPS or STW instruction in the Nios-II architecture. The STW instruction is basically the store instruction, which says that the specific given register should be read and the value in that register from the register value should be taken and stored in the specific memory address. So in this stage, the memory is written. The next stage you can basically know that it is the write back stage. The write back stage is nothing but writing back to the registers after the operation is done from the ALU. All right. So there are three types of instructions. So instructions can be majorly categorized into these three types. First is the I type, the second is R type, and the third is J type. Well, the I type deals with the instructions which have immediate values. As I said, the values which can be directly picked up from the instruction. They have the uh, actual value that don't have to get from any specific memory location. So such type of instructions are I type instructions. The second type is R type, which is register type. Now this type of instructions have only registers in them. Like for example, mult R1, R2, R3, which does the multiplication of R1 into R3 and stores it in R1. So it doesn't need any uh, specific value to be calculated. And the uh, op in all the cases is the opcode. Well, when the opcode is 3A in the Nios-II processor, we know that it is an R-type processor. And then the OPX extension decides what is to be done with the operands. That is actually the OPX decides the function of the ALU. Then the third type is J type, which is basically the jump type. All the jump type instructions come under the J type. It has a 26-bit direct um, value for the jump address and an opcode. So I've made some programs. First one of which was loop. Now this program runs a loop and adds the numbers in a sequential fashion. The test vectors were my SJSU ID, which is 10809305, and what I did was I wrote a program in assembly, and then uh, it was run on my Nios-II architecture. So now you can see over here the input is in R3 register, and it's 10809305, which is my SJSU ID. And once all the whole loop runs, it generates in hexadecimal the answer, which is 1A. Well, this is the factorial benchmark program, and it you can see over here, 1's factorial is 1, 2's factorial is 2, and 3's factorial is 6, which is correctly given in the R2 register. The third program that I tested was dot product benchmark program, which does the multiplication of a number with its, yeah, double and then adds sequentially. Again, the test vector was my SJSUID itself, and you can see the correct answer over here is 168 in hexadecimal. So concluding this presentation, I'd like to say that after implementing, we know that there are several hazards actually which occur due to pipelining, but we can always find a solution. The most popular being the forward chaining or forward data forwarding solution. I've used the data forwarding solutions in my processor. Then I also have thought about some future work. Like for example, scientists have found out some algorithms like the Maslow algorithm, which executes the instructions in out of order execution. So that is some sort of future work that you can implement using this architecture. Thanks a lot.